maybe I just stick to this, right? Is it better if I do it like okay. Okay, so that's unfortunate. Okay, so this is what I was just talking about, right? You have this image here, you have a cat, and this cat is put into a neural network, and the neural network basically decides whether it's a cat or a dog, right? So far, so good. And in most applications, what you can basically see is whether it's a cat or a dog, or maybe you can see the probability with which the neural network thinks that this is a cat. So maybe this neural network thinks it's with 0.8 probability a cat and with 0.2 probability a dog. But that's really it, right? There's no more information that you will get out of this. And so from this, you may ask the question, yeah, but why does the neural network think it's a cat, right? I mean, if you ask a human, for example, my 3-year-old son, he would tell you, well, you know, it has the eyes or the ears or something like this, and it really looks like a cat. And this is really not a question that a neural network typically will allow you to answer. And that's true for a lot of classifiers out there, basically. But I mean, like, if you think about it more mathematically, then okay, I mean, a neural network is just some affine linear transformations, and then you apply some nonlinearities element-wise. So you could say, well, okay, I have this neural network here, and I just chuck in some data, and it runs through the network, and I could just look at all the hidden units, right? And that would give me the answer, right? It would explain me why the neural network thinks that this is a cat. But the problem is it's just not useful, right? I mean, you get this humongous amount of numbers, and you look at it, and it's basically not useful for you at all. I mean, okay, so this is basically where explainable machine learning comes in, or some people say explainable AI. I don't like this term because I don't like the term AI, but basically this is what the whole field is about. You try to come up with some approximative schemes which allow you to answer these questions. They allow you to basically infer why the neural network makes the decision it makes. And there are various strategies to do this, and I'm just gonna discuss the most popular one probably, which is something called local explanations, or also known as heat maps sometimes. Explanation maps is another term that you may have heard. And the basic idea here is, so I'm just gonna explain this on this example here, basically. So we have a jet from the CIFAR-10 image data set. And we train some classifier to classify on CIFAR-10. And now basically explanation methods, these local explanation methods, they produce you something called a heat map, which is displayed on the right. And this heat map is basically assigning heat to pixels, which are really relevant in some sense for the classification result. So if a pixel is highlighted by red, if it's assigned heat, then it was very relevant for the classification. And so you can look at this and say, well, okay, it is a jet. It's classifying this jet as a plane because it has some cockpit, there are wings and so forth. And so now there are a lot of ways to generate these heat maps. I don't have time to go through them all, but I just gonna give you one example of how to produce them, which is probably the most simple one and also the most naive one, but it's also the one that I can explain very quickly. So I gotta stick to this. And the basic idea here is, so you take the classifier, and we're just gonna call it the classifier, we're gonna call it G for now, for concreteness. And then you calculate the probability that this is a plane. And then you differentiate this probability with respect to the input. This you can just do with like normal deep learning libraries and autograd, basically. You just differentiate with backprop with respect to the inputs. This is a little bit different to normal neural network training, where you differentiate the network with respect to the weights, but it's basically the same underlying arithmetic. And then you get some kind of result which has the same shape as the input, right? Because you're differentiating a function, which gives you a scalar output, the probability that this is a plane, with respect to the input. So it's an object which has the same shape as the input. And then you can visualize this with this heat map. What you typically do is you just sum the absolute values in each color channel, and you get this heat map. That's the basic idea. Now, this is just the most naive way of doing this and the most naive explanation method. There is now a lot of literature on the subject to come up with some kind of explanation methods. And this is, for example, a recent book which summarized the current state of the field, which you can check out. I also want to point out that now these methods are really incorporated into deep learning frameworks. So for example, PyTorch recently had this new addition to its ecosystem, which is called Captain. And it's really just a tool, a set of library for calculating these kind of heat maps. And so as a result, it's now very easy to deploy these explanation methods in practice. And it's going to be interesting to see, I mean, particularly for me as a researcher, how this is actually applied in the field, right, in reality. And I would be curious to hear if some of you are working on this. Yeah, so maybe you have asked yourself the question, so why is this even interesting? Why is it interesting to have explanations? And I just want to give you a quick list of things that I just came up with. There may be other reasons out there, but this is something that I personally find interesting. So one is just debugging. Often these machine learning tools don't work in the way we would expect them to work. And so this is just a tool in your arsenal, additional tool in your arsenal to, detect what could be the underlying reason for this misbehavior. Another one is feedback to users. And in order to understand this, and this is a really important issue, I think, just imagine that you're a bank and you have some credit assignment problem where your customers come to you and they want to have a loan, and you have some kind of algorithm which gives a score of whether or not you should grant a customer a loan. And so normally you just get back a score, right? But for a user, it may be important to know why he or she got a really bad score, right? For example, it would be great to get back like some kind of feedback where you get told, well, maybe you should make more money, your salary is not high enough, or something like that. And by doing so, by providing these kind of feedbacks, you can hope that you increase the trust of the users in your bank and in your algorithm, right? Because it makes the whole decision process more transparent. And then the last reason, which is getting very important these days, is that these explanations are increasingly required by law. There's now a regulation by the European Union, which goes under the name of Right to Explain, which basically says that any automated algorithmic decision process has to provide some kind of explanation with it. And so if you deploy neural networks, for example, you need to answer this question in the foreseeable future. And right now there's still some loopholes in this law. So it's not enforced in practice, but the European Union is very much working on revising this legislation, and then this will be a legal issue. Okay, so especially considering the last 3 points, you may ask the question, so good, you have shown me these heat maps, right? They are in some sense an explanation, but can I actually trust these explanations? And by trusting, I mean basically, can they be manipulated? And do they faithfully represent some kind of information about the underlying algorithmic decision-making process? These are two questions that you may ask, right? You just get presented with this heat map. So does it have any, information in it that you can trust? And this is basically the research question that I've been focusing on. One of the research questions that I have been focusing on for the last year or so. And this is what I'm gonna talk about in the rest of my talk, and try to convince you that you should take these explanation methods with a little bit of caution. It's certainly not something that you should just take at face value and just simply trust it. Okay, so I've basically written 2 papers about this over the last year. One was at NeurIPS last year and called Explanations Can Be Manipulated and Geometries to Blame. And the other one was at ICML just this year. So just a few weeks ago. And so I cannot summarize both of them. I basically gonna focus on the first one because it's just very recent and basically follow up on the first. But if time permits, I will briefly sketch what is done in the other paper. Okay, so basically, what we have shown in this paper is the following result. And I'm just gonna summarize the result on one slide, and then I'm gonna explain to you, give you some examples of what the result means in practice. And I'm gonna explain to you a little bit how we arrived at that result, because there's some theory and some theoretical understanding behind this. It's not just experiments. So basically what we have shown, and so you need to stick with me. I'm gonna try to explain this carefully, but it's a little bit complicated on first sight maybe. So basically what we have shown is that for any model G that you can give me, right, I can construct another model G twiddle. And this model G twiddle has the following properties. So first, it has identical behavior on the data. So for example, in the CFAR10 image classification result, all the classification results on all data samples of CFAR10 would be the same. And even more so, also the class scores would be the same. So the probabilities with which the network thinks this is a plane would be the same. And also all the, not only the winning class, but also the sub-winning classes would have the same probabilities. So exactly same output on all of the data, right? But you can provide me with a target explanation for any given data sample, and I can modify the classifier to this G twiddle such that it closely reproduces this target explanation map. So basically you can arbitrarily draw an explanation, and I can manipulate the classifier in such a way that it has this explanation, but that the underlying decisions that are made are exactly the same. That's the basic idea. So let me illustrate this in an example. So here we take the classic of machine learning, the classic task of machine learning, MNIST. We all love good old MNIST. And so what we have here is basically a 9 from the MNIST data set, and we train some classifier G on MNIST, and it classifies all the digits as you would expect. And then we run some heat map, some explanation method to produce these heat maps. And here you see an example in the lower left-hand corner for an explanation for the original model G, right? Just some explanation that shows you that somehow the closed loop is really important for the classification result. And now we run our manipulation method, and we take this original model G and we transform it to a manipulated model, G twiddle. And this manipulated model G-twiddle classifies all the digits in exactly the same manner. It has the same probabilities that this number is a 9. But as its explanation, we have specified it to have the explanation of a 42, which we just drew. I literally drew this in MS Paint. I know, you know, that's not a perfect tool, but and so we can manipulate the model such that it always gives us this explanation. So now you may say, okay, this is a really academic exercise, right? Why would anyone want to do this? But let me quickly motivate why this is, I think, of really practical relevance as well. And for this, let's consider the following example. Let's again consider this credit assignment task that we discussed earlier. So a bank tries to decide algorithmically whether or not a customer gets a loan or not. And so let's imagine we are this, there's this bank out there, and it's called the Sexist Bank of America. And basically what it does is it uses an unethical strategy for credit assignment. It basically just looks at the gender of the applicant. And if it's male, then it grants a loan. And if it's not, it rejects the loan. That's basically the strategy that it uses. There's a tiny bit of income in the classifier as well, just to ensure that it's not completely insensitive to the income, so that the income is a little bit different every time. The outcome is a little bit different every time depending on the income. But this is really just a tiny perturbation. Mainly it just looks at the gender. And so if you run an explanation method, it would produce you some kind of explanation which would look like the one on the left, this blue one. And I've just switched the visualization here a little bit, just because now it's feature-based, not pixel-based. So I've listed the 3 features: gender, income, and taxes. And I assign relevance, which is normalized such that the total relevance is 1. And you can see basically all the relevance is put on gender. So the explanation method shows you, it makes transparent that an unethical, sexist decision process is at work here. So you would say, great, right? So if the European Union requires by law to specify, to give these explanations, we would be able to pick up on these kind of strategies. But what we show basically is that you can construct another classifier, G-twiddle, which has exactly the same classification results. So for any given user, it would not matter if you run G-twiddle or G, the outcome would be exactly the same. But the explanations would be drastically different. Now all the relevance is completely shifted to the financial features. And that's basically why I think this result is worrisome and interesting at the same time. It basically shows that these explanation methods, as they currently are not a good proof for an ethical decision-making process, right? They're basically, they can be manipulated. Okay, so I just wanted to comment because I have this funny title, right? Fair washing explanations with off-manifold detergent. That was the name of the paper that we put out. So hopefully you have understood the first part of this title now, fair washing explanations. That's because the original strategy was not fair, and then you can fair wash it such that the explanation gives the appearance as if the underlying strategy was fair. That's basically why we called it fair washing explanations. What you probably haven't understood yet is why we fair wash with off-manifold detergent. And in order to understand this, I need to explain to you how we do this manipulation. And so in the paper, we do a lot of differential geometry to show that there actually exists such a G-twiddle and how we can get it. I will not do this here because I think it would just take too much time, and we don't want to take a 1-year course of differential geometry. That's probably not the purpose here. So I just gonna motivate this, give you the intuition of why we are able to do this, and but then you can go to the paper and see. Okay, so in order to understand why this drastic degree of manipulability is possible, we're going to take a step back and think a little bit about what we are doing when we are doing classification. And so what we are doing is basically, in most modern deep learning and machine learning tasks, what you actually have is you have some data, and this data lives on a low dimensional manifold embedded in a high dimensional ambient space. So an example of this is again MNIST. In MNIST, I think the resolution of the images is 28 by 28 pixels. So these data points, they are vectors in R28 times 28. I don't know what 28 times 28 is, but it's a huge number. So it's a huge dimensional vector space. But then if you are looking at a particular MNIST digit, you could just slightly rotate it or translate it, and it would still look like a digit. So there's some local connectedness between these images, at least locally. And the dimensionality of this space that is locally connected and is just the set of all images in MNIST is very low. I mean, estimates are order 10. That's like the estimates that we have. So there's a huge dimensional, really high dimensional embedding space and a very low dimensional data manifold on which the data points actually live. Another way of seeing this is if you just randomly, uniformly sampled pixel values, you would just see something like noise. But you would never see something like an MNIST digit. And so that's another indication.
We have two questions.
Sorry.
You answered partially from Sophie. So what do you mean by has the same result on every data point? Is it referring to finite data set, or is it valid for any possible data point of an infinite continuous space?
So our theoretic results are really for the whole manifold. So it's exactly the same manifold. And then it depends a little bit on the classifier that you're using. If you're using logistic regression, you can exactly construct this model. So it has exactly the same behavior on the entire data manifold, not just the sampled space that we have, but really the entire data manifold. For a neural network, we can only approximately construct this manipulated model. And so we just approximately have the same outputs, but to very good precision. So the mean square error between the outputs is like something like 10 to the minus 6. I mean, I would need to look at the paper, but it's very small.
Okay. Okay, we have a lot of questions popping up. So we also have from Kaushik. Not sure it makes sense, but does the work assume any smoothness assumption of the geometry?
Yes, we do assume
besides being there for
Yes.
Okay.
So we are assuming, technically, so you need to look at the paper to really see all the assumptions, but one of the assumptions is that the data manifold is a smooth manifold. That's an assumption that we make.
Perfect. I also got a question from George Speiser. Under the European law, how does a company justify classification? Is it using an importance image like you showed? Do we have to go into the trouble of creating a TLG, or can we just send a fake importance image?
So I'm not a lawyer, so whatever I will say now, take it with a grain of salt, right? Don't sue me if I'm saying something wrong here. But my understanding is that right now these details are still clarified, because right now you can basically get around this regulation by saying that there was some kind of human in the loop. If there was some kind of human in the loop, you don't have to provide this explanation. And so now it gets a legal question. It gets to be a legal question about what does it mean to have a human in the loop. And right now, my understanding is from talking to people who have analyzed this, that the definition of this is very liberal. So in practice right now, you basically don't have to worry about this. This is my understanding. You should talk to your lawyer if you want to be sure. But the European Union is working on a revised legislation, and then it will depend on the details.
Okay. I will go through the other question and tell me if you think that we should go to the end for some or so. From Itya, does the manipulation of explanations apply also to other explainability methods other than these local methods?
So we haven't tested other global methods, mainly because there it's sort of training is built into the explainability often. So you typically train a model such that it has some underlying understanding of concepts and so forth. So it's a little bit of a different way of approaching the question. So it doesn't fit into the framework. But what we did test is that it holds about for a lot of different local explainability methods. So you can check the paper. I think we had like 6 explanation methods in there, but we also, we just included 6 because, at some point the paper, you have to have tables for all these methods. We tested it with more, and at least qualitatively, it also worked for the others that we checked.
Finally, how is the information preserved while approximating manifolds? Basically, how do you quantify the information loss? Yeah,
so maybe we can talk about this in the end, because I was planning on discussing how we estimate the manifold. So that's a great question. All of them were great questions, thank you. But I think this one will become clear in just a second, if I have time for it.
And if not, please ask the question again, please. Okay.
Cool. Well, thanks so much. It's good to get some feedback. Just remember, basically the upshot here is that the data lives on a low dimensional manifold in a high dimensional embedding space. So the technical term for this is the manifold hypothesis. This is sort of the name that is assigned to this phenomenon. And so now just to mentally picture this, we're going to draw the ambient space as being 2-dimensional and the embedding manifold, the data manifold, as being 1-dimensional. That's not true in reality. The data manifold is much lower dimensionality than the ambient space, but we cannot picture this, so we will stick to this mental picture. And now we're going to pick a particular data point, this red dot here. And remember that the heat map as an explanation is of the same dimensionality as the input. So it is a vector in the ambient space, right? Because the ambient space is the space of the inputs, basically. And so we can attach this vector to the data point, just draw a little arrow. And now observe that the behavior of the function on the data just determines the components of the gradient along the data manifold. So in order to understand why the gradient is important, just remember that one of the explanation methods was the gradient with respect to the input, right? So the arrow that I've drawn here for illustration is just the gradient with respect to the input of the classifier G. And that's a vector in ambient space. And I can decompose this vector in 2 components. Oh, no, I need to. The green one and the yellow one. One is parallel to the data manifold and one is orthogonal to the data manifold. And so now the gradient component parallel to the data manifold is the only component that is relevant for the behavior of the function along the data manifold. Basically because you just need to know what values the function takes along the data manifold, right? In order to know its behavior on the data. And that determines the gradient along the data. But the components orthogonal are completely arbitrary for the behavior on the data. I can arbitrarily change them. It will not change the behavior on the data. I hope this was clear. If not, please interrupt me. And so basically what we do is we manipulate these orthogonal components of the gradient in order to manipulate the gradient explanation. Because we can arbitrarily choose these orange orthogonal components, we can basically arbitrarily choose an orthogonal component and thereby manipulate the gradient, so the explanation. And because there are much more orthogonal components, the explanation is basically determined by the orthogonal components. And so to very good precision, we can reproduce any target explanation map. That's basically the idea. So I hope this was clear. In the paper, we really show this with differential geometry. So we start from a function defined on the data manifold, and then we show that we can extend it and manipulate the gradient orthogonal to the data manifold. Okay, so this is just saying what I just said. And here are a few more pictures. So we are seeing again C410, and we are seeing the original model and the manipulated model, G-twiddle, and you are seeing basically that this manipulation works for several different explanation methods, grad, input times grad, and so forth. If these names don't make sense to you, it's just different explanation methods. Okay, so I'm at 32 minutes, I think. So I could stop here, or I could quickly explain how we propose to reduce the number of the degree of manipulability. I'm not sure what the time frame is.
Okay, we have another question, but I will propose to continue as we have the question on the flow. So if okay, some people want to ask questions, they can directly do it. So there's another question at this. So will there be any usefulness to look at second order gradients? Maybe how the gradient changes if you change the data.
Yeah, this is something that we are investigating a little bit. There is some degree of manipulability for the second order gradients as well, because essentially, again, you are just fixing the function on the data manifold, right? This is the function on the data manifold is fixed, but the orthogonal components are not fixed. And so if you calculate the second order gradient, the Hessian, then a lot of these components of the Hessian is not fixed just by knowing the function on the data manifold. But there are components that are fixed, and so you could look at these. The problem is it's harder to visualize, right? With like the gradient, you can really show this heat map, so it's something that you can intuitively grasp. But with higher order derivatives, it's harder to picture. That's basically a problem. So maybe I just quickly explain. So in the paper, we also propose a method to reduce the amount of manipulability that you can do. And I quickly gonna explain this. It will take like 3 minutes. I should say up front, it's not the most practical one. It's more like something that we can work towards and make aim to make it work at scale, but it gives additional proof to this mental picture that I outlined here. And basically the idea here is, you know, the orthogonal components of the gradients were arbitrary, right? We could choose them at will, but the components parallel to the data manifold were not arbitrary. So our idea was to basically project the explanation on the components parallel to the data manifold. Now the question is, the problem that makes it so hard to do this is basically that we don't know any analytic form of the data manifold. We just have samples, right? And we need to infer the structure of the data manifold from these samples. And so this makes a connection to a whole other field in machine learning, which is called manifold learning. I'm not going to go into details here. I'm just gonna give you the most basic algorithm that there is to estimate this. And this can be used on MNIST, for example. And so the basic idea is here, you pick a data point for which you want to calculate the explanation method. Then you look at the k nearest neighbors and you fit a hyperplane through these neighbors. And this gives you some estimate of the tangent space. And then you project the explanation on this tangent space. That's basically the idea, right? And so if you do this, so you project it, and this is the result if you do this for CFAR10. So basically, this is the original model, and this is the manipulated model. And the explanations before here for the manipulated model looked like a 42, and now they look very similar to the unmanipulated model. There's still some degree of difference due to the, well, one reason is that we don't estimate the manifold perfectly, but the manipulability is basically the manipulated thing goes away, and it's also harder to attack directly. Okay, so I'm over time, so I just gonna summarize here. So what I've tried to convince you of is that explainability methods as they stand, local explainability methods, are vulnerable to a very serious degree of manipulability. So specifically, we can construct, for any classifier G, we can construct another classifier G twiddle, which has exactly the same behavior on the data manifold, but has an arbitrary explanation. And in principle, you could try to get around this by projecting the explanations on tangent space. The problem with this is you need to estimate tangent space. And for high dimensional data sets such as ImageNet, this is an extremely costly task and something that is still very much an active research topic. Okay, well, thank you very much.
For the German way. we just got to a question from Alaska. How is information preserved while approximating manifolds? Basically, how do you quantify the information loss with respect to original data samples?
Yeah, so I mean, there are two problems here. One is we don't have the entire data manifold in practice, right? I mean, you can construct toy models where you know the data manifold, and there are also some robotics tasks where you know what the manifold will look like. But for image classification, for example, we just have samples of the underlying data distribution. And the task is now to infer the structure of the manifold from these samples. And this is inherently ill-defined, right? Because if you wanted to construct a manifold which goes perfectly through these points, you would get a lot of solutions, and many of them are really wiggly. And so, you know, you need to come up with some kind of regularization scheme, but it's just that the underlying problem is it's a task that has no unique solution. And you can hope that you can somehow, you know, that is the typical problem of machine learning. So this is one problem. And then the other problem is that even if we knew the underlying data manifold perfectly, it's still a very computationally intensive task, right? And so we will never fit tangent space perfectly. And so these two sources very much lead to information loss, right? It's not that we can perfectly estimate tangent space, and because we can, it's a very difficult problem, but also we cannot perfectly estimate the manifolds. So there's very much an information loss there.
I got a good question from Elena. Assume that the sexist bank simply replace its model by the non-sexist G tilde. Will that mean that both models are equally good, and hence there is also no problem with the sexist model?
So the model G and the model G twiddle, they have the same performance on the data set, right? They give the same, like if you go there and you submit your credit form, you will get the same answer back, exactly the same probabilities. I mean, in this case, if you do logistic regression, which is the most straightforward thing that you would do there, you really get exactly the same thing. There's no approximation involved. And so the behavior on the data manifold is exactly the same. What is not the same is the explanation, right? And so somehow the bank can still run exactly the same strategy because it's, well, if it wants to, but the heat map is really not displaying that the strategy is used. And that's the danger, right? Because if you naively apply these heat maps, you would think that this is impossible, and you would take these heat maps as a proof that the bank is not following the strategy. Of course, in this particular case, it's just 3 features, right? So you could just shoot different proposals at the bank and see that this is basically the strategy. But in reality, you're not using 3 features, you're using much more, right? And so you can hide this in more subtle ways.
Mm-hmm. Great. Sorry, I'm going through. And I get a question. So the explanation G seems to be what we will expect intuitively. Is there maybe a measure like entropy of the different explanation? Are the intuitive explanation special in some cases?
Yeah, I mean, of course, if you pick very crazy target explanations, I mean, that's a really good point. And then of course, the answers are so nonsensical that it will be like, you can always go back in the case of the credit assignment task, right? You could always go back and just try it out. If you have 3 features, you can just try it out. And so if the target explanation is chosen completely crazy, then there are probably ways to check this. But if the input becomes really high dimensional and your target heat map is a little bit more subtle, then it may be hard. And there are now more and more papers on the subject of trying to detect these kind of manipulations. And I expect this to be something that people will work on over the next years. And hopefully we will come up with some kind of good algorithmic modifications which will be able to pick up on these manipulations. And entropy might be one way to go.
So a question also from Henry, I think it's also this question: could you detect manipulation based on the orthogonal components? So
yes, so this is an idea that we have also been exploring a little bit. I mean, basically, because the orthogonal components are not determined by training, you could try to look at them and look if they look like noise, right? You would expect if they're not determined and the training process does not try to manipulate them, they should look a little bit like noise. But so I think that would be a strategy to look at this. But the problem is, in practice, you need to estimate tangent space, right? And for MNIST or CIFAR, you can still do this, but for higher dimensional data sets, it's just not feasible at the moment. And so then you cannot really do this decomposition. And so for low dimensional data sets, I think that's a good strategy, but for high dimensional data sets, it's just not something that we can do at the moment. That may change.
Okay, any other questions? We might have time for 1 or 2. Otherwise, I have one, but
I also have one sort of a silly question, maybe.
Those are the best questions, actually.
I mean, in your presentation, you presented it really nicely to as an image. Like the explanation was given to us as an image, as like a heat map. So my question would be, could we use some type of image classifier that classifies the right explanation? In a sense, I mean, imagine you have some data set, and the data set gives you some heat map, which is an explanation. But on the other hand, we know exactly which explanation is the true one, or this could be politically mandated, which explanation is good. And then we could just apply some type of image classifier, which says, hey, is this explanation modified, or is it the actual explanation that is supposed to come out?
Yeah, so I mean, like there was a very interesting paper at ICML this year, which basically trained, so it was something called along the lines of right for the right reasons or something. And so what they did is they basically trained a classifier in such a way that it not only got the right classification results, but they also ensured that the heat maps look sensible. So they had some human operator who drew some heat maps. Basically, they said, well, in this region, most of the heat must be assigned. And then they train the algorithm such that the heat maps look correctly. And that was interesting, I found, because I mean, in some tasks, they also showed that this helps with generalization. This was a very specific task. I don't think that you can expect this on ImageNet, but in this very specific task, it was a scientific task, I think, related to skin cancer. It helped with generalization. Yeah, I'm not sure if that is the general thing. I would doubt it. So maybe the paper was called differently. I'm not quite sure if it was called right for the right reasons. It's sort of I would need to look up what the precise thing.
Okay. I think we will finish. I just want to conclude to say a big thank you.
Well, thank you.
That was really great. So I will stop the recording now, and so we'll have a small break.